Today, we're diving deep into the amazing account of how this massive rock formed and became the only place where life thrives in the universe. A huge chunk of rock and water hurtling through space, unlike any other planet out there. What makes Earth so special? It's the only space haven in the cosmos where life exists. But how did this amazing celestial body come to be? Join us as we unravel the fascinating science behind Earth's creation, from clouds of gas to the birth of stars and the chaotic beginnings of our planet. We'll uncover the mysteries that made Earth capable of supporting life. I'm Mike Adams, and welcome to All Things Space. In today's video, we are exploring how did Earth evolve to support life. The Earth, a colossal mass of rock and water hurtling through space, stands unparalleled among known planets. Its unique distinction lies in fostering life, making it not just our dwelling, but the sole sanctuary in the universe. We've assembled some of the latest research to uncover the profound processes that birthed an Earth conducive to human habitation. Within this vast cosmic expanse, there is only one hospitable haven for humanity. The Earth appears custom-made just for us, offering sustenance, water, food, and air, all essential for our survival. We depend entirely on this singular abode, yet 5 billion years ago it was non-existent. The current position of Earth in the Milky Way galaxy was once occupied by a vast cloud of gas and dust. This intriguing tale chronicles the metamorphosis of that dust cloud into the planet we now inhabit. Astronomer Thomas Fleming, well versed in the intricate process of planet formation, employs telescopic observations, such as those at Kitt Peak in Arizona, to decipher the Earth's origins. It all commences with a colossal cloud comprising gas and dust particles and minuscule components akin to dirty grains of silicone and sand. These regions, termed molecular clouds by scientists, differ vastly from the clouds we witness on Earth. Molecular clouds, vast expanses shaped by remnants of exploding stars, host elements like iron and silicon. These cosmic remnants form the building blocks for new stars and planets within these clouds, drawn together by gravity's force. Over millions of years, these clouds contract due to gravity, accelerating as they collapse. As the collapsing cloud shrinks, its center heats up, birthing stars just like our sun. The remaining material flattens into disks, fostering planet formation such as Earth's origins. Until recently, the mystery of dust evolving into planets puzzled scientists. However, a pivotal discovery arose from an unexpected experiment conducted by astronaut Donald Pettit aboard the International Space Station in 2003. While filming the interactions of granular substances in zero gravity, Pettit observed these particles forming clusters, a revelation crucial to understanding how planets formed billions of years ago. Recognizing this breakthrough, astronaut Stan Lee grasps the significance of these clumping particles, unveiling a fundamental phase in planetary evolution in a weightless environment. In the early stages of Earth's formation, rapid particle aggregation likely occurred, leading to the creation of larger celestial bodies. Within a remarkably short time frame, akin to mere seconds on a clock, these particles combined, forming planets through a series of violent collisions and mergers. Earth emerged approximately 30 million years into this phase, enduring intense heat and a barrage of space particles, rendering it uninhabitable. At this juncture, Earth was an absolute inferno, surpassing temperatures of 8,000 degrees Fahrenheit, unsuitable for any life. The planet also faced peril from charged space particles, further complicating its potential for sustaining life. This snapshot encapsulates Earth's tumultuous early evolution, highlighting the drastic transformations necessary for it to become the habitable planet we know today. Meanwhile, space scientist Rodney Derrick monitors the sun's eruptions, which generate energetic particles forming the solar wind. These particles, traveling at astonishing speeds of 1 million miles per hour towards Earth, pose severe threats to astronauts and even aviation if detected in excessive amounts. Monitoring these solar events is critical to alerting individuals and organizations of potential hazards, as these charged particles can prove lethal to living cells and cause havoc on planets during intense solar storms. Earth's protective shield, the atmosphere, shields it from space's harsh conditions. Mars's fate, stripped of its atmosphere by the solar wind, showcases this danger. Earth's salvation traces back to its early formation. As the planet formed, intense heat separated elements, forming a protective molten core. Daniel Lathrop of the University of Maryland investigates this shield. His focus is how Earth's core, a dynamo of liquid iron, generates a magnetic field. This shield, extending into space as the magnetosphere, deflects solar wind particles. Those that breach it create the stunning aurora phenomenons that we see. Despite ongoing erosion from the solar wind, our magnetosphere shields us, preventing significant atmospheric loss. Though Earth loses its atmosphere to the solar wind, it's a slow process, posing no immediate threat to life on our planet. The Earth's magnetic field, powered by its iron core, was crucial for its development, creating a protective shield from the solar wind. In the first 6 minutes of a hypothetical 12-hour Earth history, the planet lacked breathable air and water and resembled an inhospitable environment. An impending collision with another planet was set to change everything. This colossal impact would liquefy Earth, creating debris that eventually formed the Moon. The Moon, 15 times closer to Earth initially, shaped our planet's seasons and became a vital part of its evolution. Scientists, through the Apollo missions and later simulations, uncovered that a planet-sized body collided with Earth, leading to the Moon's formation. This cataclysmic event reshaped Earth's axis, setting the stage for life as we know it. Additionally, the creation of the Moon influences tides, which were much stronger initially but have since weakened as the Moon gradually moved away. The existence of oceans, fundamental for life, was not present initially, raising questions about the origin of Earth's water. At its early stages, the inner solar system lacked liquid water, with the nearest water reserves located around 160 million miles away in the outer asteroid belt. The mystery of how water traveled from these distant regions to Earth is a puzzle that scientists are only beginning to unravel. One exploration involved the NASA spacecraft Deep Impact to study a comet named Tempel 1. The mission aimed to uncover whether comets, which had previously been theorized to deliver water to Earth, indeed contained significant amounts of it. The impact on Tempel 1 confirmed the presence of water in comets, but further analysis of their water composition have not fully matched Earth's oceans. Despite this discrepancy, scientists continue their quest for answers. Rather than solely relying on comet delivery, a new hypothesis is emerging, suggesting that the outer asteroid belt might have played a role in transporting water to our planet. This ongoing pursuit to understand Earth's water origins remains one of the most intriguing mysteries of scientific exploration. In Western Canada, a blazing meteorite streaked across the sky, witnessed by many. Local photographers captured its trail after it entered the Earth's atmosphere. Breaking into numerous pieces, it landed on Tagish Lake in British Columbia. Scientists swiftly recovered frozen remains from the lake, revealing the best preserved meteorites ever found. One such piece was sent to NASA for analysis, revealing it remained remarkably intact despite heating during atmospheric entry. Meteorites have spent millions of years in space, retain extreme coldness, heating up only briefly upon entry. Contrary to popular belief, they don't cause fire upon impact, but cool rapidly. Fragile meteorites like the one found in Tagish Lake typically disintegrate, but their landing on a frozen lake preserved them. Analysis unveiled that 20% of the meteorite's weight consisted of water trapped in clay minerals, similar to those found in everyday soil. Tracing its trajectory back to the outer asteroid belt, astronomers theorized that asteroids from this region delivered water to Earth, possibly contributing to our oceans. Jupiter's gravitational pull likely disrupted asteroid orbits, causing them to collide with Earth, releasing water upon impact. Recent studies of ancient rocks and zircons suggest Earth acquired its water within a remarkably short time frame, possibly less than 150 million years after formation. This influx of water transformed Earth, shaping its oceans and atmosphere into what we recognize today. Around 4.4 billion years ago, just 25 minutes on a 12-hour scale after Earth's formation, the planet looked drastically different, with a denser atmosphere and iron-rich oceans. Although conditions were suitable for life, the lack of oxygen in the atmosphere remained a significant barrier to human survival. In its early stages, Earth faced intense upheavals and storms. Over time, this activity subsided. However, even 500 million years after its formation, the planet was ocean-covered and devoid of oxygen in its atmosphere. Without oxygen, life, including animal and human, couldn't exist. Geologist Martin van Kranendonk explored how Earth obtained its oxygen. His research led him to Shark Bay in Australia, a site hosting ancient stromatolites, rare structures crucial to Earth's oxygen creation. These stromatolites, present in only 2 locations worldwide, have been growing for millennia, producing oxygen through photosynthetic bacteria. This process was instrumental in creating the Earth's current atmosphere, which is essential for diverse life forms. The belief that stromatolites generate Earth's oxygen stems from a groundbreaking discovery in North Australia's remote Pilbara region. Here lie the oldest fossils ever found, the ancestors of Shark Bay's stromatolites dating back billions of years. These fossils hint at life emerging soon after Earth's formation, eventually leading to an oxygen-rich atmosphere supporting complex life forms. However, this increase in oxygen wasn't immediate. Despite stromatolites existing billions of years ago, oxygen levels remained stagnant for a considerable period. The reason for this lies in the banded iron formations discovered in Australia's Karijini National Park. These formations, created around 2.5 billion years ago, resulted from microbial activity interacting with iron in the ancient oceans. Oxygen produced by stromatolites reacted with iron, forming rust that settled as rock, trapping vast amounts of oxygen over time. It took nearly 2 billion years for the atmosphere's oxygen levels to rise to a point where animals could survive, making a turning point in Earth's history. Finally, around 500 million years ago, the atmosphere became conducive to sustaining animal life. Thanks for joining me on this exploration of how the Earth evolved to support life. Until next time, stay curious, keep exploring, and I'll see you in the next video.